The second situation is liquid flow down an inclined plane. So this situation is different from the situation number one, because in situation number one, the plane is on a horizontal direction, horizontal plane. So means that the water, the liquid will not move. That's why we need the upper plate being pulled by certain force to move the liquid. So in this situation, so we only have one plate, and then on this plate we have liquid like this. So and then this liquid will flow down like this one due to the gravitational force. So all the calculation is actually same with the previous one that I explained previously. So from that one, we take the velocity profile, and then we solve by using the boundary condition here. So and then again here we assume that there are no pressure gradient. So because the flow here, it has free surface. So the pressure is constant, so means that we have dPds is equal to 0. So and then again, if you want to draw the velocity profile here, okay, sometime you could draw like this one, but sometime if the depth is very high, okay, you maybe need to draw like this. So this is the changes of velocity in velocity profile, and then you need to draw the area where the velocity is constant, because if the depth is very high, very depth, okay, the velocity actually stop changing at certain height from the bottom plate here, and then from this point the velocity will remain constant. Okay, because sometimes if you have a wrong impression in your flow, okay, so maybe you need to you put your calculation, or you do your assumption in Navier-Stokes equation is wrong. Okay, later on we will discuss about the formation of velocity profile like this. It will create another phenomenon called the boundary layer. Okay, so we focus on this first. So and then we have this situation. So and then what we do is we could use the equation number one. So and then we substitute all the parameter, and then we could get this one, because the parameter of the parameter of pressure and so on. So we have this one. So and then if we neglect the value of pressure here, so we could get this one, negative gamma over mu sine theta. So here I think you could understand all the terms here need to times with P and need to time with gamma Z. So the gamma Z here means the multiplication of rho and G. So we call it as a specific weight. So this is gamma. Okay, so it is equal to rho and G. Okay, so if you see here, gamma Z mean rho, G, and H. Mean Z is the depth actually. So means it's show the pressure according to the depth of the water. So and then we substitute the boundary condition. So again, this boundary condition you must taken from the original situation. So for example, we have the situation like this. So we have 2 points here. This is one boundary point, and this is another boundary point. So here it is the boundary between the liquid and the solid, and this is the boundary between the liquid and the air and the gas, the atmospheric pressure. So here the trick is we take u equal to 0 at y equal to 0. So this is quite straightforward. You could get, you could have it. But the second one here, okay, the trick is because in this situation, the velocity at this surface is not given. So it is different with the previous example where the velocity of the upper plate is given. So in this situation, we could trick like this. So means that we assume that at that point, at top point there, the du dy is equal to 0 at y equal to d. So this means that at y equal to d, mean this is the coordinate of y axis, the du dy is equal to 0. So the du dy here means the changes of u was stopped. So it means start from here, okay, so there are no changes of u in terms of y axis. So this is the trick for this one. So and then to have this one, so we need to integrate, we could have this, okay, if you substitute to solve this one, so we have this equation, so and you know that this we have 2 times differential form. So means that if we integrate it once, so we could get du dy. So we integrate, we bring the dy to the right hand side, so we get one terms of y, so we have negative y here. Negative y gamma over mu sine theta plus c. So this is the constant. So I hope here you could understand, because we already discussed how to do the integration for this term. So and then we apply the boundary condition at this one. So we know that du dy is equal to 0 at y equal to d. So we substitute the d here. So and then, so when u is equal to capital U, it can be assumed that du dy is equal to 0 because there are no velocity gradient anymore. So means that at this time, okay, we assume that the small u can be changed into the capital U, because we assume that this is maybe the maximum velocity. So normally, if later on when we learn about the boundary layer, so we will assume that this is equal to capital U, which show the free stream velocity. So and then if you substitute everything, so you will get that the value of c, the constant that we need to find here, is equal to gamma d over mu sine theta. So we substitute the equation, so we get the du dy is equal to this one. So and then what we need to do is the du dy, we bring again the value of y to the right hand side here. So and then we integrate for the second time, so we get this term. You could see that the value of y is increased one step, so we have another y, and the y here will become y squared. So and then we get another constant. So and then we put the boundary condition, so we have u equal to 0 at y equal to 0, and then the value of c is equal to 0, and then finally we could write these terms. So here if you read a few textbooks, you will find that sometimes people use the idea of kinematic viscosity, the symbol of mu here. Okay, I'm sorry, this is the nu, and this is the mu. Okay, the sound is miu, mu, and the sound is nu, niu, nu. Okay, so but if you write the sound, it will become mu and nu. Okay, so the idea is mu is equal rho nu. Okay. Okay, this is the okay, so this is the relation. I'm not sure. I just confused just now. Okay, so it might be mu is equal to rho nu. I'm sorry. Okay, so this is the idea of rho and mu and nu. So I hope you may check this one. I just confused. Okay, so means that I hope you could understand. Sometimes people use kinematic viscosity, and sometimes people use dynamic viscosity. So and then people will try to get the U maximum. So normally in that situation, because the flow is laminar, later on I will describe about that. So it is equal to, if U is maximum, so for sure we assume that it occur at Y equal to D. So we substitute into the previous equation. So we will get that the mu is U max is can be written as this one. So gamma d square over 2 mu sine theta. So and then if you want to calculate the overall flow rate, so the volume flow rate is Q is equal AV. So the idea here is you need to do the integration, because if you see if this is the plate, okay, so and then you have the velocity profile like this. Okay, so means that you need to understand that the velocity is different from along the y-axis. So mean you cannot just take one velocity and then you multiple with the cross-sectional area to get the total flow rate. So you need to do the integration because the velocity is varies. Okay, so the idea is to integrate this one is Q, the flow rate, is the integration from 0 to d u dy. So u dy here means the velocity, the local velocity at certain point here, okay, multiple with the area of this one. So and then we assume that the area here is the y height, y length here is dy, and the width here is unity. So we just write as dy times 1. So we substitute the value of u max here. I'm sorry, the value of u, the small u here that we get. Okay, so and then we have the u here. So we do the integration. We put the limits 0 to d. So and then we get this one. So and then we could have the average velocity in integer, means in number, okay, by dividing with area. So with area here again, we have a flow like this. So we assume that the thickness is y, and then the area, the width is 1. So we just y here is equal to d. Okay, so and then we just divide by d times 1. So then the power of d is reduced from 3 to square, like this one. So and then in certain verification from experimental and calculation like this one, some people replace the idea of sine theta with tangent theta, because the value is not so much different. So in small slope, so it's still same, could give us the correct answer. So and then if we replace the sine theta with the tangent theta here, so we will get this value, g d square sine s naught means tangent theta divided by 3 nu here, the kinematic viscosity, and then we could calculate the average situation by using this equation. Okay, why we replace the tangent theta here? Because it is not easy to normally this idea is used in open channel. Okay, as I said, right, in open channel problem, and it is used by civil engineers. So civil engineers then normally use the idea of the distance and the height of certain place. So that if we know the distance here and also the height, so we could calculate the tangent. It's much easier for this one. So and then if we calculate the Reynolds number, okay, as I said, it's verified with the experimental work. It is found that if the Reynolds number is larger than 500, so the flow is become turbulent. So for Couette flow, so it's only can be used for laminar flow. So and then you need to make sure that the Reynolds number is not exceeding 500 for this situation. Okay, as I said, this is called the open channel problem. So in real open channel problem, so for sure the flow is turbulent, then the velocity profile is actually a little bit different. So in lamina, it is okay for us to assume that the velocity profile is like this, where the top location here is the maximum velocity. However, if the flow is become the velocity is higher and higher, and then it's become a turbulent flow, actually the velocity profile will change into this one. So it still have velocity at the top, but the maximum velocity is actually occur at 1/3 from the top here. So this is the if you study the open channel in real means not in small scale, because it will give us the a turbulent open channel. So the maximum velocity will occur at location almost 1/3 from the top surface. So means that if you see river and so on, actually the maximum velocity of a river is not on the surface but at 1/3 the depth one third from the surface. Okay, so the relation of that one is actually 1 over nu is equal to rho over mu. So means that mu is equal rho nu. Okay, I'm sorry. Okay, so the simple one is you could see from the Reynolds number equation. So let's say we have Reynolds number is written as rho Vd over mu, and sometimes it's written as Vd over nu. So from here we could conclude that rho over mu is equal to 1 over nu. So means that the rho nu is equal to mu. Okay, I'm just confused just now. So this is the example. If we have a crude oil, kinematic viscosity 9.3, SG mean specific gravity. I think you already know this one. This is about the density compared with water. So mean 0.92 mean it is 0.92 times the density of water. So it will about 920 kilogram per meter cube. Okay. So flows over a flat plate that has a slope of s 0.02. If the depth of flow is 6 millimeter, what is the maximum velocity and what is the discharge per meter of width of plate? Determine the Reynolds number for this flow. So we just take the velocity profile u as this one, and then we assume at y equal to d, the maximum velocity is 0.038. So mean we substitute all of the value in this equation, and then to calculate the discharge per meter of width, so we could have 1.52 times 10 to the minus of 4 meter square per second, and then the Reynolds number is Vd over nu, so it is equal 1.63. So the flow is laminar.